All right, so what did we talk about last time? We talked about Euler integration and how terrible it is. And you should never do it. Just don't do it. It's bad for you. We talked about energy ideas. And so everyone's seen that before, kinetic potential energy, but the kind of hopefully newish stuff that we talked about there was this idea of using energy functions to investigate stability, right? This idea of Lyapunov stability, Lyapunov functions, which are kind of generalizations of energy. And if you can find one of these things and prove that, trajectories are, at least constant or going downhill, then you can prove stability. And the Lyapunov stability is basically the gold standard. It's super powerful and it proves like global stability kind of results. But often it's hard to do that. So then we also kind of looked at these ideas of local stability a little bit. We just started that at the end. And this is the idea of looking at the linearization, the local linearization of your dynamics, and looking at the eigen, or we're going to do that today, looking at kind of the slope of the, the tangent to the curve in 1D, right? And this idea of like that slope, just the sign of the linearization tells you local stability in some neighborhood, right? Okay, so that was last time. Today, we're gonna finish off that local stability discussion. We're gonna now sort of generalize that to n-dimensional, Rn kind of stuff. So the general case. Then we're gonna talk about, then we're gonna start talking about ODE integrators. So we're gonna go into a little bit more, like basically, I told you Euler is bad. Now I'm gonna tell you what the better things are. And so we're going to start out by talking about what are called Taylor integrators, which are the oldest numerical integration methods. And it's sort of what it sounds like. You basically use a Taylor expansion about your current point to sort of step yourself forward. So those are very old. They work, but they have some sort of negative aspects to them. They've actually had a resurgence in the last 10 years or so because you can do some cool things with them. You can actually do really cool error propagation kind of stuff with them. Fun fact. But what is basically the gold standard now are these things you've probably all heard of called Runge-Kutta methods. So who's heard of Runge-Kutta methods? Like everybody. Who's used a Runge-Kutta method before? Everybody. Like everybody's used? No, not everybody. Okay. You may have without knowing it. So if you've used like ODE 45 in MATLAB, or any one of these ODE solvers, if you ever simulated a system of ordinary differential equations, odds are you used the Runge-Kutta method. That's basically what all of them are. Okay, so we're going to talk about like how you get those things and like some of their properties and all that kind of good stuff. Yeah. Oh, thank you for that. I do not mean to have a waiting room on there. My bad. Hello, Zoom friends. Sorry for missing this waiting room thing. Okay, cool. Rusty on the Zoom stuff. Okay, cool. All right, so we'll get into it now. So let's talk about this local stability stuff a little bit more. So last time we did this in one dimension. And when I say one dimension, I don't mean 1 degree of freedom, like in the mechanical system sense, right? I mean 1D state space, which is a very, very simple thing. The like actual mechanical analogy for this would be like something like a heavily overdamped system. So like, a 1 degree of freedom system would be like a brick sliding on ice, on the line where the state is position velocity. To get to a 1D state space, you have to like do something else. So like the mechanical analogy there would be if you had really, really high damping. And so you could basically assume that like things only moved if you pushed on them and that like they reached terminal velocity almost instantaneously. So think like brick sliding in like honey or something like this where you push. So then you can like skip the acceleration stuff and just have velocity. That's kind of what this picture is. So imagine like super over damped such that you can ignore acceleration and things just stop when you stop pushing on them. That's like the intuitive picture of what's going on in terms of the dynamics, right? Okay, so we drew this picture where, when we talk about how in 1D you can plot, the state lives on X and the dynamics, are f of X, and we can just plot everything like this. And we drew this picture with like this roughly cubic looking, f of X. It's nonlinear, but we talked about, the equilibrium points are the zeros of f of x, where x dot equals 0. And then we talked about how the slope of this guy indicates its stability. So if the slope is negative near at an equilibrium point, like it is on this middle one, that means if you're perturbed to the left, you're going to get pushed to the right and vice versa. So that's stable. If it's negative slope, and then if it's positive slope, like these other two, that means if I perturb to the left, I'm going to keep going to the left, right? And vice versa. So this guy is unstable. And this guy is likewise unstable. And so what we're going to do, okay, so if we kind of write those things down, right, we end up with the following conditions. df dx, evaluate the equilibrium point, which we'll call x star. If this is negative, this is locally stable. And again, these are local results in the calculus sense of some epsilon ball, right? And these things don't tell you how big that epsilon ball is. It could be big, it could be uber tiny. All it's saying is in some little tiny neighborhood, it's stable. Okay, and then we had, if this thing is positive, it's unstable. And then we kind of talked about the weirdo case where if it's exactly 0, this is inconclusive. You can't say anything in this case. And this is basically one of the limitations of this linearization story. You just can't say anything. And we drew those 2 examples last time of a local cubic where it's flat. And then you can, just from eyeballing, you can say, if it goes this way, it's stable. If it goes the other way, it's unstable, right? But you can't tell that from the linearization.
Is it for equilibrium point? Is it for equilibrium point for the inverse real?
The equilibrium point is the f of x equals 0. So all of these are equilibrium points, right? And this is, we're talking about now df dx, which is the slope, right? So if the slope is negative, we're stable. So the positive, we're unstable. If the slope is 0, we can't say anything from the linearization, and you have to look at nonlinear terms. And there's ways of doing that, but generally speaking, that means you have to do something nonlinear and look at a Lyapunov function of some sort, and it gets a lot harder. So this is one of the limitations. Yeah.
Is there a second method test kind of thing?
No, not really. So what you would do in that case probably is just start using Lyapunov ideas. So what I would probably do in that case is try writing down a Lyapunov function, like a quadratic Lyapunov function, and take a second order Taylor expansion of the dynamics and smush that all together and see if I can come up with a local Lyapunov function on the quadratic model that works, right? So you can play lots of games with these ideas. There's also another set of stability ideas that are basically, so the lines between once you go nonlinear, once you go past this, the lines between Lyapunov and whatever else are blurry. There's this other set of ideas that are basically this sort of idea of a nonlinear generalization of this. It's called contraction theory, but it's super closely related to Lyapunov theory. It's basically like a local differential version of a Lyapunov function. And it would amount to essentially what I just said of taking a local quadratic, Lyapunov function and blah, 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 and trying to find something that worked. So basically though, kind of past here, if you're in this situation, you're in sketchy, uncharted waters kind of territory, and you're gonna have to get clever and come up with something yourself. There isn't a canned, it just works plug and chug method. And this stupid thing locked itself, and now I have to, okay, cool. Okay, that's the story. So yeah, if you're interested in something, contraction theory is kind of interesting. It's basically more of the Lyapunov story. It's a variation on that theme. Okay, cool. So now what we're gonna do is generalize this to Rn. So actual systems, robots that we care about that live in higher dimensional state spaces. Okay, so what happens in Rn? What happens if I'm not in 1D anymore? What does df dx become now? Jacobian matrix, right? In general. So this is f of x maps us from x to x dot, right? So in that context, it's got to be a square matrix, right? The input and output dimensions are the same. It's the state and state derivative. So this thing is now Rn by n. This is a Jacobian matrix. Oops. And what we're going to do is, unsurprisingly, we're going to take this thing and we're going to take an eigen decomposition of it. Reason being, now that we've taken the eigen decomposition, basically we've decoupled it into a whole bunch of 1D systems where the diagonal eigenvalues are basically a bunch of 1D systems. Then we can just use the 1D result on each of those, right? Does that make sense, everybody? Okay. So here's what that looks like. And so, yeah, totally unsurprising. If all of the real parts of the eigenvalues of df dx evaluated at the equilibrium point are strictly negative, then you're locally stable. So they all have to be negative, right? In all the directions, basically, is what this is saying. And then the other story is if any, so this is all of them have to be negative. If any one of them is positive, then you're unstable. So the idea there is, so you could think maybe, oh, there's only like one eigen axis or one eigenvector along which it's unstable, and it's stable in all the other directions. If I were to pick a random point, if there's noise in the system at all, basically, if you have any randomness, any noise at all, which there always is, right? There's going to be always some component along the unstable axis given noise, and that's going to blow up. So basically, there's no way you can ever sort of, hope to be stable in real life if any one of these is positive. That's kind of the story. And then the same sort of thing here. If any of these is equal to 0, you're in that inconclusive case. Okay, any questions about this? Is that idea of doing the eigen decomposition and basically decoupling into a whole bunch of 1D eigen systems, that cool with everybody? Yeah.
Is this what you explore to do like
It's not really. So like that stuff is sort of related to this. Those are ideas from linear systems. Generally there, you're actually dealing with, so there you're dealing with a feedback system, and the whole idea there is you're trying to like move the eigenvalues around to have like, basically there you're trying to shape the eigenvalues of the closed loop system, right? To be nice in various ways. So that's like a design tool for making these be in certain places. And there's more to, like, this is just a binary sort of thing, right? Root locus is like a sort of, I'm moving these things around and I'm trying to shape the eigenspectrum to be what I want, right? To get desirable closed loop dynamics. So this is a little bit simpler and like dumber than that in some sense. This is like a binary, you check this to see if it's going to blow up on you or not kind of thing. It's a lot less rich of a picture. But this is like, the idea here is this, we're doing this like about an equilibrium point in a nonlinear system, right? So this is like using linear ideas to try to tease out information about a nonlinear system also. Okay, anything else on this? That's cool with everybody? All right, so what we're going to do now is like kind of crank through this for the pendulum, because it's everyone's favorite nonlinear system. It's pretty intuitive. Okay, so the pendulum, the dynamics are f of x equals theta dot and then minus g over L sine theta. And last time we talked about the equilibrium points of this thing being at 0 hanging down or at pi straight up, right? Those are both equilibria, and we all know intuitively what those things are, look like stability wise. Let's write down the Jacobian here. So this is df dx. So this thing is a 2x2 matrix because it's a 2-dimensional state, right? And so what this is telling you is for some little tiny delta x, this is what's going to happen locally around x star, right? Okay, so so I'm going to take partial theta dot, partial theta is 0. partial theta dot is 1. Partial theta double dot, partial of the bottom row with respect to theta is minus g over L cos theta. And then partial of that bottom row with respect to theta dot is 0, because there's no damping. So this is it. Okay, so now we can just plug and check. We can plug into this guy and check the eigenvalues, right? So let's check the upright equilibrium. And we all know that thing is unstable, right? If I give it a little nudge, it's going to fall over intuitively. So for the upward, theta equals pi equilibrium, we get df dx. I'm just going to plug in cos of pi. It's -1, so I get g over L over here, and 0. I can take the eigenvalues of this 2x2 matrix, which you can do actually by hand. It's not too bad for 2x2. I'll just write them down. So these guys are plus and minus root g over L. So because one of those is positive, it is unstable. Everyone follow that? Cool, easy. Okay, let's do the down one. This one we get df dx is 0, 1, and then this guy just changes sign at the bottom, right? So this is minus g over L now. So we do the eigenvalues. And now we get 0 plus minus I root g over L. So this is pure imaginary, right? So in the strict sort of sense, this is inconclusive. You may have remember if you took a linear controls class, right? Like sometimes this is called marginally stable. That's like this linear systems idea for a real linear system. Super bogus when you generalize to the nonlinear case. So that's not a thing. So we can't really say anything about this. But we already did last time the Lyapunov proof for this guy, right? So we know based on the Lyapunov function, aka checking the energy, we know this is Lyapunov stable, right? So kind of what this is saying is, what this says in the linear picture is that this thing's going to oscillate forever. And it has no energy dissipation. There's no real part, right? The real part is blow up or damping. The imaginary part is oscillations. And this is actually the oscillation frequency, right? Does everyone recognize this as like omega for the simple harmonic oscillator? So this is basically how fast you wiggle, and this is how fast you damp or blow up. That's intuitively right. So this thing's not damping or blowing up. It's oscillating forever at that frequency. But we know from the Lyapunov function, which was nonlinear, right, that this thing really is going to oscillate forever and not go anywhere. Okay, cool. Cool. Okay, any questions about this? This is like bread and butter stuff. Like this is super useful, and you'll use this all the time to like sanity check. You know, is your closed loop system stable? Is, you know, all that kind of good stuff. The Lyapunov stuff is a lot trickier to use. This you can always do, right? It's kind of trivial. So it's probably the most useful thing. Okay, so I think the last piece on the stability stuff that I want to do, all of the stuff we've done so far was on like continuous time, you know, F equals ma type dynamical systems. What we're going to do now is take a look at this same stuff in discrete time. So this would be if I already had a simulation that was like xk plus 1 equals f of xk, sort of time stepping me in discrete time. What does this look like? And it's pretty easy to come up with like a parallel result. So let's see. So this would be like after I'd already done, you know, Runge-Kutta or something. And I have something that looks like this, right? Where the F now maps me to the next state at T plus H instead of X dot. In this context, so we said in the continuous case, you want X dot to be 0 to have an equilibrium point, right? So that's a 0, right, of F. How about like here? Yeah, so equilibrium point here is if xk plus 1 equals f of xk, right? So that, I don't know what that's called when a function spits back the same thing you put in. I mean, in general, if it does that for any input, it's an identity. How about if it does it at a particular point? It's called a fixed point. That's right. So that's so yeah, the definition here for an equilibrium is f of x star equals x star, and this is called a fixed point. So yeah, roots or zeros and fixed points are kind of dual to each other in a certain sense and are related. Okay, so to think about stability here, what we want to think about is an iterated map. So basically, you know, so the idea here is this thing spits back the same result all the time, right? So the idea of stability is if I were to like plug in, oh, let's write this down first. So the idea here is like if I were to simulate this for a long time, like n time steps, this is like f of, right? Like f of dot, like f of x naught, right? I'm gonna call the f a whole bunch of times. Now I have to remember how many parentheses I put. Okay, cool. So is that clear, right? I'm like iterating this function. I'm calling it on its own output a whole bunch of times. So the idea here with stability, like if you think about this a little bit more, right? The idea of stability says if I perturb x naught, or like if I'm here, let's say x naught, let's say I plug in x star plus a tiny perturbation epsilon, right? If this thing's stable, the idea is that if I plug in a little epsilon here, and then I run this thing a whole bunch of times like this, it should convert back to x star if it's stable, right? Does that make sense? So let's write that down. Stable implies that limit as n goes to infinity of xn, which is equal to this iterated map thing, where I call f a bunch of times. And then here I'm going to plug in x star plus epsilon, plus a tiny epsilon. That this limit equals x star. And then this epsilon is some small number. Or a small, you know, small vector, whatever. So for small perturbations, we end up back, right? That's what this says. Okay, so if that epsilon is small, the reason I did the small thing, sort of obvious. What I'm going to do now that I assume that thing's small, I'm going to Taylor expand this guy, right? In epsilon. So I'm just going to do a first order Taylor expansion of that iterated map thing. So if I chain rule through this whole thing, what do I get? So f of x star plus small epsilon is approximately f of x star, which is just x star, right, by definition. And then the first order Taylor expansion, df dx evaluated at x star times epsilon, right? That's my first order Taylor approximation. If I plug that into the big iterated map, and I chain rule through this guy, what's it going to look like? I'm going to get just a whole bunch of products of these guys, right? For each. So this is going to say then xn is approximately x star plus df dx evaluated x star, that Jacobian at the equilibrium point, to the n minus 1 power times epsilon, right? that clear to everybody? That's just doing the chain rule through this guy, this Taylor expansion, right? df times df times df is that chain rule through, right? So what I want then is this thing to converge back to x star as n gets big, right? That's that limit. Is that clear to everybody? Am I making sense? Okay, so what does this thing have to do then in the limit of n getting really big for this to be true, right? So if this limit works out, that means this term has to go to 0 in the limit, right, of big N. So what has to be true about my Jacobian then? What's smaller than 1? Basically, it's saying this matrix to a big power has to converge to 0, right? This whole, because this has to be true for any epsilon. Let me write that in. So that means the matrix has to go to 0, right? Because it has to be true for any epsilon. And for that to happen, yeah. Exactly, yeah. So this is called the spectral radius sometimes. Basically, yeah, the eigenvalues, which can be complex, right? They all have to have complex modulus or like norm, right? Less than 1 for this to go to 0, right? Does that make sense, everybody? Okay, so in discrete time, so yeah, I should say this has to be true for all epsilon. So the set of conditions here then are if all the norms or modulus of these guys, of these eigenvalues, if all these are strictly less than 1, we get local stability. Then if any are greater than 1, we get the unstable thing. And if any are exactly 1, we get the inconclusive case. And hopefully this makes a little more sense here, right? So if this comes out to exactly 1, what that's saying is, this linearization picture, I did this Taylor expansion in epsilon, assuming epsilon is small, right? So in that picture, this first order Taylor result, this might go to 0, right? But if epsilon is finite, I'm basically skipping all the higher order terms in the Taylor series there, right? When I did this to get this result. So basically what's happening is if this drops to 0, well, then the quadratic term and the cubic term are the next ones that are going to show up, and those are going to do something, right? And if I'm only checking this, I don't know what the higher terms are going to do. And they could absolutely blow up or shrink down, right? You just don't know. So does that make sense, everybody? Okay, so discrete time, you check the modulus of the eigenvalue, and it's, you want less than 1 to be stable. Continuous time, you check the real parts of the eigenvalues, and you want those to be strictly negative for stability. Is that cool? Everybody good on this? Okay, so yeah, this is what you do if you were finite diffing a simulator directly, or you had some black box simulator, or you had some system that's already discretized in time. The other stuff is what you do if you have the continuous ODEs, right? So this discrete time thing does happen a lot though, right? Because we numerical simulation, but also our controllers are usually digital and in discrete time, right? So this is the kind of thing you end up with a lot. Like if you plug a digital controller into your system, you're in this kind of situation, right? Okay. Any questions about this? All good? Okay, yeah.
Is there discrete and
Yeah. So we're actually going to do that in a little bit when we talk about integrators. It's exactly what you expect. So right before we checked v dot negative in the discrete setting, you check delta v has to be negative, right? It's just over a discrete time step. So it'd be instead of v dot, it's vk plus 1 minus vk if you're stepping through, and that has to be negative. So the discrete continuous stuff is all super analogous. You can do all the same things in either case, and it generalizes exactly how you expect. You check deltas instead of dots, basically, right? So yeah, we'll do that in a. This is super annoying. Okay, here we go. All right, everybody good on stability stuff? This is super useful stuff. I feel like this is things you should know about. Hopefully you've seen some of this before. Okay, so now we're going to go back to like the integrator story now that we know some things about stability. So we're going to talk about higher order integrators. Basically, not Euler integration anymore. So we did the so we did explicit Euler before this, or forward Euler sometimes it's called. And if you kind of think about this a little bit, it's actually equivalent to just taking a first order Taylor expansion of f of x of t of the dynamics at your current x, and just using that to approximate your solution. So let's write that down. So remember what we did. We did x k plus 1 is equal to, or yes, this is equal to x tk plus h, where h is our time step, just by definition, right? And then the Euler integration thing is we approximate this as xk plus dx dt, which is equal to evaluated at xk times our time step h. And this is just right. If we think about what this is, right, dx dt is f as our dynamics function. So this is h times f of xk. So this is exactly our. So I literally just wrote out the first order Taylor expansion of x of t, and then if you look at it, it is exactly an Euler step, the forward Euler step that we did last time to do Euler integration, right? Okay, so Euler integration equals first order Taylor expansion. So that the obvious thing, if I say, kind of like told you this is terrible and we showed you how bad it is, last time. So if I'm just looking at this now, the obvious thing to do would be to just take some more terms in this Taylor expansion, right? To try to make a better integrator. So let's try that out and see what happens. And this is, in fact, what people did at the dawn of computers in I don't know, the 1940s or whatever. So we can, sort of do this. So we get, it's x at tk plus, if I just keep rolling with the Taylor expansion. So there's the Euler term. There's Euler integration. I'll take the next term. I can take the cubic term if I want to, right, and just keep going. Okay, so what I want to do, so I just wrote this super generic Taylor expansion out. Now what we want to do is plug in f for these derivatives, right, and actually look at this in terms of the dynamics function to see how to actually implement this. And there's a slight gotcha. Okay, so if we do this, this is easy. The first one we already know is just f of x. The second one, let's look at that. So if I chain rule this, that's d dt of f of x, right? So now if I kind of chain rule that guy, I get that's partial f partial x times dx dt, which is equal to partial f partial x times f of x. And this partial f partial x guy, that's, we know that, right? We've used that already a whole bunch. So that's no big deal. We know how to get that. Let's do the next one. So if I chain rule this guy, you know, unsurprisingly, I get d dt times the stuff I already did. Up there. And if I really like kind of chain rule this now, I have to do this guy from the f again, and then I'm going to get this new term here, which we can talk about. Okay, so that's it. I just like chain ruled the whole thing, blah, blah, blah. Okay, remember f of x is in general a vector function, right? It's Rn. So this guy, we already saw this guy. That's a matrix. That's a Jacobian matrix, n by n. What's this guy? E squared f dx squared. It's a Hessian, but it's a Hessian of a vector value function, right? So let's think about this. So f eats a vector, spits out a vector, right? If I take its first order Taylor expansion, I get a matrix, right? Because that's what that's saying, right? Is I need to plug in a little delta x to get out a delta f of x, right? Like a delta x in. So that's a matrix, right? The second derivative now, if you think about that, what that's saying is I get to plug in 2 delta x vectors to get out 1 delta f output, right? So this thing, it turns out, is a third rank tensor. So when you have a vector valued function, like the intuitive way to think about it is like for each derivative I take, I get another like tensor dimension or rank. Because what I'm doing here, right, this is basically saying like in scalar land, you know, this gets multiplied by an x squared, right? What's x squared when you have a vector? When x is a vector, it doesn't really exist. Or what it actually is a tensor product of the vector. You don't, right? And so that means basically what happens here is like, another way to think about it is it's got to get multiplied by 2 delta x's to spit out an f, a delta f. And the way that works in vector land is you get another dimension on your matrix. So I'm basically multiplying in a delta x from like 2 sides now, and I have to get out a delta f still. So this guy's a third rank tensor, i.e. a 3D matrix. If I go to the next derivative, if I try to take a third derivative, it's going to be a fourth rank tensor, like a 4D matrix, right? And it keeps blowing up and getting bigger and bigger and like more expensive to compute. And that ends up not being awesome, sort of unsurprisingly. So this guy, third rank tensor. Or has anyone worked with tensors before? This is like a pretty standard thing in machine learning and statistical, like it's called it's this multilinear regression. If you do like large statistical models, you see this stuff sometimes. I mean, it's literally TensorFlow is where the name comes from, right? So it's a big thing in statistics. It's also a big thing in machine learning. It's just like higher dimensional versions of matrices, right? So think third rank, the matrix also has a bunch of slices going, you know, this way. Okay. Maybe people have seen this. Who's actually like used tensors before? Hands, handful. Okay, not a big deal. That's what's happening. We're not going to like do too much more of this. I'm just telling you where that's coming from. Yeah, we have a Zoom hand. Is that just I've played with these before? I see him. Okay, cool. So so here's kind of the deal with this Taylor integrator stuff then. Like we can do this. We can definitely take this Taylor expansion, like we just said, as long as f is smooth and these derivatives exist, right? So do this forever if we want to. And we can go, yeah, as long as you want. But it turns out this whole tensor business means these start to get really expensive to compute as you go to higher orders. So these are not very popular. So you can imagine that's quite painful to do in general. Past like basically past here, So like second order is no big deal. We can do that already. Third order, you got this tensor stuff already, and like past that, kind of forget it. Okay, so the key thing, so this is of historical interest. There also is some like state-of-the-art stuff that uses these still, because it turns out like having a local high order Taylor expansion to map like errors through is sort of useful in general, but generally these are not used for simulation anymore. But this does set us up for this nice thing that is useful, which is called the order of accuracy of an integration method. So the idea here is when we write down these ODE solvers, we often, you'll hear this thing, this order thing. And what this is saying is just the number of Taylor series terms that the integrator matches. And so the idea is we're not going to use these Taylor expansion methods to solve the ODE, but we want these newer methods to still match the Taylor expansion well to give us a good solution is kind of the idea. So sort of obviously from this whole discussion, Euler is a first order method. Like by definition, it is the first order Taylor expansion, right? So it turns out Euler is a Taylor integrator, sort of trivially. Okay, cool. So we said we don't want to do this tensor crap, but we still want to do okay in terms of matching the Taylor expansion. Yep.
What is the definition of matches here?
You will see very shortly. We're going to do it. It's literally that the solution that the thing spits out. So xk plus 1 coming out of the ODE solver should match this Taylor expansion out to however many terms. That's the order of accuracy. So we're going to do it right now. So here we go. So the where this takes us is Runge-Kutta methods, which are the standard ubiquitous thing that everyone uses, and I'm sure you've heard of these. So what these things do is say, okay, the Taylor idea is I take xk and I Taylor expand it and I ride along the Taylor expansion to xk plus 1, right? The idea with the Runge-Kutta method is we want to achieve that Taylor expansion, result. But we want to do without computing that Taylor expansion explicitly. And the idea is like pretty intuitive, actually. What we're going to do is think about this as like, okay, what's a Taylor expansion? It's a polynomial, right? So you can think about the Taylor expansion as giving us a polynomial between xk and xk plus 1. And I can get that from doing a Taylor expansion at xk. I can also get it from evaluating f at a whole bunch of points in the middle and like fitting a polynomial through the points, right? So the key idea is instead of Taylor expanding at xk, I'm just going to take a bunch of f evaluations over the interval and fit whatever order polynomial I want through the points, right, through the f's. So it's like almost like polynomial least squares fitting, basically, right, to a bunch of f evals. Okay. So yeah, there's some other terminology then. The number of f calls. that you take over a time step is called the number of stages. And in general, the number of stages is not the same as the order. They can be different. Okay, cool. And there's actually some hard results that say past a certain point, the number of stages has to be strictly greater than the order. All right, let's see. Okay, so let's ask a fun question. What is the best we can do with a single stage, aka a single F eval, aka linear interpolation, right, over a time step? Because that's all we can do. If we only have one F. Let's see what we can do. What do you guys think? If you had to guess. Yeah. So if I told you you're only allowed to have one evaluation of F per time step, like what do you think the best you can do is?
First order.
I would think first order, right? Euler. So that's like kind of what you think, but it turns out, let's find out. Let's do it. All right, so what we're going to do is we're going to Taylor expand this guy. And so the key idea here is you have a degree of freedom in this. You can evaluate F wherever you want over the interval, right? So explicit Euler, I evaluated xk. There's other versions of Euler. Well, let me write this down and we'll talk about it. So here's what I can do, right? I can evaluate this thing anywhere on the interval. So let me write that down explicitly. And so alpha is right between 0 and 1. So this is saying, you know, that all this is doing is interpolating between xk and xk plus 1, right? Letting me take where I evaluated F along the interval. Okay, so here you go. So what I'm going to do now is just Taylor expand that thing. So there's the Euler step right there. And then I'm going to get this second order term. And then, you know, higher order that I'm not going to bother with. Okay, so basically for any alpha, I'm going to match the first order term, right? So it's saying I can pick whatever alpha I want, I'll get at least a first order method. How about if I want to make this thing second order? What is alpha? What does this term have to have? What's constant needs to be here to make this actually the second order Taylor expansion? Well, okay, definition of Taylor expansion up here. So what does it have to be? It has to be 1/2, right? So it turns out if alpha equals 1/2, I get a second order method. So this shows you can get a second order method with only one stage, with only one F call, which is like, you know, kind of interesting and not what you would have expected. And this has a name. Does anyone know what this is called? It's called the midpoint method. And you may have seen this before. This is actually a specific, let's say a couple of things. So, okay, if alpha equals 0, that's just xk, that's explicit Euler, that's what we did before. If alpha equals 1, that means I'm evaluating this at xk plus 1 at the endpoint, right? That's called implicit Euler. And probably you've seen that, and that's actually quite common in robotics. A lot of simulators use that. And I can pick kind of other weird in-betweens, right? But it turns out exactly at 1/2, I get this magic second order thing. Okay, so this is called implicit midpoint. And we'll spend some quality time with this guy because it's actually quite special. So here's what it looks like. Basically, I evaluate F at the average . So here's here's the question. How do I solve? So I know xk, right? I plug that in. When we did Euler, I just plug in xk, cool, and I got xk plus 1. How about now? How do I solve this thing for xk plus 1? I know xk, I plug it in, that goes here and here. I want to solve this for xk plus 1. But that's buried inside f here and over here. So what do I do? Huh? How? What do I do? You could. We could talk about that. If I just straight up want to solve this equation, though, what do you do? Exactly. So you're going to do some kind of root finding method. I'm going to move this over. I'm going to set this whole thing equal to 0, right? And now I have a root finding problem. And I'm going to use Newton's method to solve this thing. So this is why it's called implicit. So in general, we have explicit methods and implicit methods. Explicit means like Euler, I just plug xk in and I get out the xk plus 1. Implicit means I've got the x at the next time step buried inside of f somehow. And then I can't just like, then I have to do some kind of root finding or whatever to find the next time step. And there's sort of lots to say about this. So that's called implicit. We need to solve for xk plus 1. Okay, so who's done Newton's method before? I think you do this in RoboMath, among other places. So we'll kind of handhold you through this. So here's the idea. Actually, move this down here. New page. Okay, so here's Newton's method. The idea is, so Newton's method is a root finding algorithm. It says, if I have some function, so I'm going to write this down as R so we don't get confused. So it's a root finding method. That means it finds zeros of a function, right? Roots. So I'm going to write this down as R of xk plus 1. So R here for residual. So the idea is I'm just going to take that equation up there that I want to solve and move everything over to the right so that it's supposed to be equal to 0. And I'm going to call that thing that's supposed to be 0 R. So that's going to look like this. Cool. So this thing has to equal 0 for like the for this to be the, basically if this thing equals 0, then I've got the right xk plus 1, right? I just moved over everything to one side up there. So what I'm going to do if I don't know xk plus 1, remember this is like a nonlinear equation, it's gross, I can't just solve it in this form. So what I'm going to do is take a guess at xk plus 1. And for these integrators, I can always guess xk for xk plus 1. So I'm going to start with a guess of xk plus 1 equals xk. I'm going to Taylor expand this guy like so. And this is approximately R of xk plus 1 plus dr dx evaluated of xk plus 1 times delta xk plus 1. And I'm going to set the Taylor expansion equal to 0. So this equation I can solve because this is now a linear equation and this is a matrix. So I can solve this one for delta xk plus 1. And it's just minus dr dx inverse times R. So I do that, and then I set xk plus 1, which was my last guess, equal to xk plus 1 plus delta xk plus 1. And then I do this until it converges. Cool. So I make a guess. Oh yeah, other note. Cool. Any questions? So yeah, I make an initial guess of xk plus 1 equals xk. And then I just do this. I take the Jacobian, solve for the delta x, tack it on, and then just loop that. And generally, it'll take 3 or 4 iterations for this to converge to machine precision, actually. So it converges really quick. You only have to do it 3 or 4 times. If it doesn't converge in like 4 or 5 iterations, then something's wrong with your setup. That's sort of, yeah. Okay, so the downside of this, right, is with the explicit methods like explicit Euler and stuff, that was cheap. I just plug in and evaluate F once and go. Here, I have to evaluate F a bunch of times, and it's Jacobian, right, to do this Newton thing. So it's a lot more expensive. Okay, so here's back to, someone said this already, so let's like, so any questions on this? Root finding, Newton. This is gonna be on the first homework, so you will have to implement it and try it. Newton's method is like bread and butter stuff. Like it is all over the place. You will do it forever. You should definitely know it. You should definitely like do it a handful of times. Okay, so here's the next trick we're gonna play. So this is good in a bunch of ways. We get second order, blah, blah, blah. That's nice, but it's annoying because we have this root finding thing and it can be expensive. So let's try another trick. So we're going to try now what's called explicit midpoint. The idea is we want to avoid the root finding. And we're going to use someone's suggestion. Who said this? Yeah, so we're going to evaluate x at the midpoint using Euler. So we're going to take an Euler step to the midpoint, and then we're going to plug that midpoint in. So we're going to approximate the midpoint, right? So the implicit one uses the exact midpoint, and it solves for it with this root finding. We're going to do a dumb approximation to the midpoint and see if it still works. So yeah, hint, hint, it works because we're talking about it, right? So here's what we do. We do xk plus 1 is xk plus h. And then this is supposed to be f evaluated at the midpoint. I'm just going to plug in a half step of Euler in here to get to the midpoint. And kind of intuitively, the reason this might work out is that, remember, all we care about is matching up to the second order term in the Taylor expansion, right? So this is definitely not the same midpoint that you get from that one that's doing it exactly. But as long as it matches up to second order in the Taylor expansion, then we're good. So what we're going to do now is just check. So we just tried this out. This seems like a reasonable idea. Let's actually go check the Taylor expansion now and see if it matches. So we get xk plus 1 is approximately xk plus h f of xk plus, and if I go and like stare at that a little bit and chain rule through, I'll get h squared over 2 df dx f of x plus higher order stuff that I don't care. So it turns out it does in fact match. Okay, so that is second order. Yeah,
Sorry, what are you taking? Taylor's
of this thing right here,
just of the f of xk.
the whole thing. So I've got xk everywhere in here, right? So it's explicit. I just plug in xk and I get the answer.
Right.
And all I'm doing is I'm going to Taylor expand this. So I get this guy, and then if I Taylor expand it again, I'm expanding in T. And I'm chain ruling through this guy. So yeah. So it's like I'm going to get df dx. So yeah, you can think about it as in H actually too. You want to basically see what comes out to in H, right? So if I just Taylor expand this, I get H times this guy is the H term, right? And then if I Taylor expand this guy, I get df dx times the Taylor expansion of the step inside, and I get another H over 2 times this f. So I get H squared over 2 here, and I get this guy's df dx times this guy, right? And then the next one, if I keep going, I'm going to get higher order terms. So if I just kind of plug and chug, I get the H squared term ends up looking like this, right? So it matches up to H squared. And then after that, I don't care. Okay, question now is, how many stages is explicit midpoint? 2 stages, exactly. So I plug in here, and then I take the answer from that, plug it into F again. So I get 2 F of L's. Okay, cool. So that's our little tour of Runge-Kutta methods. Let's do some stuff. Let's see. Let's run some code. I can find said code. Where is code? Yep. So they're both. These are all Runge-Kutta methods. Like almost basically everything is a Runge-Kutta method. Anything that isn't a explicit Taylor expansion that's like calling F a bunch is a Runge-Kutta method. And you'll hear there's a million variations on Runge-Kutta methods. There are Runge-Kutta Nystrom methods. There are Runge-Kutta Munthe-Koss methods. There are Runge-Kutta symplectic Runge-Kutta methods. Like everything's a Runge-Kutta method essentially. Essentially anything that calls F a bunch and like gets you an approximate solution is a Runge-Kutta method. Okay, where is? I'm gonna fire up Julia. So here's I guess maybe I'll do this over here so we can all. So this is what Julia looks like when you fire it up. I'm gonna fire up Jupyter. Just gonna show up in a web browser somewhere over here, apparently. Let me grab that for us. Right. Okay, cool. Here we go. So let's fire this guy up. So Jupyter, cool. This is maybe going to take a while. It's annoying. Hopefully not. So Julia, hopefully everyone's like, it's not too bad if you haven't used it. It basically looks like MATLAB. We're using a handful of packages here. So we're using PyPlot, which is the matplotlib from Python, and 4diff, which is one of the best things ever. Just automatic differentiation so that you don't have to handwrite derivatives, which is glorious. So we're gonna use that. Here's our pendulum dynamics from last time that we all are uber familiar with now. So now we're gonna write down a bunch of those integrators that we derived. So here's the Euler step from last time. Here's the Taylor integrator. So this does, I get the Jacobian by calling forward diff. And basically, we're going to call this df dx Jacobian A, because that's what it's generally called in control, right, in linear systems. So that's that. Then here's the Taylor integrator that we just wrote down. So this is literally just the second order Taylor expansion. So get xk h times f of x, and then 1/2 h squared, that Jacobian A times f of x, right? That's what we wrote down. Now we're going to write down implicit midpoint. So here we get xk. We're going to write down that residual function. So I just move over everything to one side. So I set my guess equal to xk, right? That's what we said. And then here's that's the residual function. then this is Newton's method in here in the loop. So what I'm going to do is I'm going to check this residual. And I want the maximum absolute value in that vector to be less than 1e minus 12. So I'm basically trying to solve it in machine precision. Here's the Jacobian of the residual function. And then here's, delta x equals minus r inverse little r. That's exactly what we just wrote down, right? And then this guy, I add on the delta, and now I've got a new residual, and I check it again, and I keep checking, right? Here's explicit midpoint. I take a half an Euler step to get this x mid, and then I plug x mid in and take the full step. Right. So that's obviously cheaper than this one that's looping and using forward diff and all this other stuff. Then these guys are just going to simulate stuff for like n time steps. All right, let's do something here. Okay, so let's plug in like 50 hertz, 10 seconds. Let's make it 20 hertz, maybe a little bigger. So we're going to simulate for 10 seconds. I'm going to start this off at 30 degrees, so like not too far up, right? Just near the bottom. And I'm going to basically evaluate all of these, the solution with each one of these integrators. So we got Euler, Taylor integrator, implicit, midpoint, explicit midpoint, all of them. And this should be no surprise. If we look at this, it should look sane, hopefully. And then I'm going to plot a bunch of stuff and take a look at what happens. That's very slow. So this is MeshCat. This is like fun animations. And I don't know, this isn't particularly insightful. So we'll just play it once and then I won't bother again because it should be sort of obvious what's going to happen. But it's very slow the first time it runs. Julia uses a just-in-time compiler. So like the first time you call a function, it compiles it and it takes a while. And then the second time it's super fast. Okay, so that's obvious. We all kind of know what that's supposed to look like. So let's go plot all these and see what's going on. So, okay, what's going on here? So the blue one is Euler, and it's garbage, as we sort of saw before. Then all these other ones are these second order methods. They're all second order, right? So we have Taylor to second order, implicit and explicit midpoint. All three of the other ones are second order, and they all look really good, right? They all basically are right on top of each other matching. Maybe I'll be a little nicer. Let's set the time step to be a little faster. That's why I, let's see, where did I put that? Okay, well, we'll be nice and make it like 50 hertz to try to make Euler suck less. And I won't bother with this, and we'll just go plot these again. Okay, cool. Okay, so, oh, that's not, okay, so Euler is still blowing up, but it's not totally off the rails yet. And then all these guys look pretty good. Let's kind of hide the Euler one for a second and look at the other ones. So yeah, these are all like basically right on top of each other, almost exactly matching. That's really good. And then the Euler one sucks. Let's go look over. Okay, so now what we're going to do is plot the energy. So I'm evaluating the energy over time for now all four solutions. I'll plot that. So let's see what's going on. So Euler sucks. All the second order methods down here look pretty good by comparison. What I'm going to do is hide the Euler line because it's sort of so terrible. And we're going to look closer at the second order ones. Okay, so these are much, much better, right? The energy is increasing out in like the 4th decimal place. But check this out. So these two are explicit Euler and the Taylor one. So those guys match really well. Their energy trend is about the same. These guys have energy blow up on this conservative system. So over a long time, they will blow up, but the rate of blow up is like squared better than the Euler step, right? So it's a lot better. But check this out. Look at this bottom line down here. Which one's that? That's implicit midpoint. So implicit midpoint is like basically conserving energy on long time. It ripples a little bit, but it doesn't have this like growth trend, right? It's actually conserving energy more or less to like machine precision, essentially, right? So there's something very special going on with the implicit midpoint method that is not going. So they're all second order. These are all 3 second order. If I look at the solutions, they eyeball right on top of each other. Let's actually go make the time steps big and try this, right? So this was 50 hertz. Let's be mean. Let's make it 10 hertz. See what happens. And I won't, again, I'm not going to bother with Euler because it's going to be super garbage. Let's go look at the solutions. All second order methods, now they start to look a little different, right, at 10 hertz. But you'll see that like the implicit midpoint one is actually, so basically Taylor and explicit midpoint are right on top of each other on this green one. And the orange one, and you can see they're starting to have some energy blow up at this level, right? Let's look at the energy. Okay, so they basically track again, energy-wise, they're doing the same thing. and the solutions match pretty much. But look at this, implicit midpoint down here is flat on the energy curve, even with really big time steps. It turns out I can make those time steps quite large, and this picture is going to stay the same. Anyone have any thoughts on what's going on there? Has anyone seen this before? This is very fun. Okay, this will be fun for next time. So there's another kind of fun thing we can do. We got like 5 minutes, right? Okay, so let's try one more fun experiment. So this is 10 hertz. It's super slow. I might put this back to like, let's put it back to like 20 hertz. So it's a little more benign, or we'll go 50. Cool. What I'm gonna do now is, and we'll talk about this next time a little bit. Okay, so here's our pendulum dynamics. I'm gonna go ahead and throw in some damping. So this would look like, I don't know, like minus C times. Oh yeah, one of the other cool things about Julia is you can write LaTeX in it. So I can actually write theta dot. So let's make this C. Let's try this and see what happens. So run it again with that damping, right? And this should sort of do, same things. It should damp out energy, right? Cool, that looks reasonable, right? This is kind of what you expect. Energy is decreasing. And they all track, they all match, right? Okay, so I'm going to do something sort of mean now. I'm going to jack up the damping constant. So let's make it like 20 and go run these again. So what intuitively is happening here, right? This thing should just fall down really slowly with a really jacked up damping constant. And this seems like it should be pretty benign. Yeah, that's fine. What's going to happen? Okay, so this is still good. They still match. I'm going to be extra mean then. So that's just like dropping like this slowly, right? That's what that solution looks like. Let's try 30. I want to break it. So I'm going to do that. And I'll make the time steps a little bigger too, just to be extra sure I'm going to break it. So we'll run the same thing. Let's see what happens now. Yeah, so that's what's happening, right? Let's look at let's plot these. Oh, it's still good. Okay, I need to be extra mean then. Maybe 10 hertz will do it. There's a extra mean. Yeah, so cool. Yeah, there we go. Okay, look at what happened now. So this is, let's try turning them off so we can see what's going on. Yeah, so that's one of the midpoints, or that's Taylor. This is implicit midpoint. Implicit midpoint still looks good. Still does the right thing. And that's the one I animated because I knew this. But the other two, the explicit midpoint and the Taylor one, blow up and do crazy things, right? So these guys blow up in the energy. And then let me just turn, but like the, yeah, blowing up stuff, implicit nails it. So there's some very special things happening with the implicit midpoint. It conserves energy. And when I add this crazy amount of damping and the other ones blow up because the time step's like too big or whatever, somehow that one's still rock solid and like doing the right thing. So more to come. This is like the enticement for next time.
The tune on the antenna cell?
Yeah. So, I mean, like you saw what I did, right? Like, so it's, I mean, hint, the other two are explicit, right? And this one's implicit. So there's something special about the implicitness of it that's going on, right? So it has like apparently like super good energy behavior, right? It's like conserving energy and stuff. And it's super stable. So I can have really big time steps, really big damping and stuff like this. Like you would think the damping is super benign, right? That just makes it super slow and like do this, right? When I add big damping, it makes the other ones blow up. So there's something weird happening there, right? But the implicit ones like doesn't care. It's totally stable. And it does the right energy behavior. So that's fun. So we'll delve into that next time. Okay. Thanks, guys. Catch you later.